What's up, everyone? Today we're going to do a little bit of an intro to radians and how to use them to find the arc length and the area of a sector. So let's get into it. So just like there are different measurements, units of measurement for length or for volume or whatever, there are also two different measurements for angles. We've seen degrees for a while now, but there's also another measurement called radians. And just like it says here, a radian is defined by the angle subtended at the center of a circle of radius 1 and arc length 1, as shown in the diagram here. So the radius and the arc length is 1, and that equals 1 radian. You can also think about radians in terms of degrees. There is a way to convert them, but we're going to talk about that later. So pi radians is equivalent to 180 degrees. That means half a circle is equivalent to pi radians. So it's just to get you an idea of what radians are. We're going to talk more about them in later videos, but for now, we're just going to talk about them in terms of arc length and area of a sector. So we have these two different formulas, again, both given to you in the formula booklet on page 7 or PDF page 8. The length of an arc when the angle measurement is given in radians is just the radius times whatever that angle is, as long as it's in radians. The area of a sector, we have 1/2 times the radius squared times that angle when the angle is in radians. So now we just have to make sure we're reading carefully. Is the angle given to us in degrees or is the angle given to us in radians? Well, let's do a couple examples using radians. Right, in this example, the diagram shows a sector of a circle with radius 5. So this length from A to F is 5, subtended by an angle of 1.1 radians. So two things. Number one, they say in the problem that it's 1.1 radians. You can also tell when an angle is given to you in radians if you don't see the degree symbol. That's an easy way to tell as well. And this sector is inside a rectangle with length 6 meters. So not to be misunderstood over here, this distance from A to D is 6 versus the radius from A to F or A to E alone is 5. So that's where the difference is there. In part A, we're finding the length L of arc FE. So they labeled it two different ways, L or F to E, but we're finding this length using those formulas, or one of the formulas from the previous slide. So the length of an arc when I'm in radians is the angle times the radius. So in our case, 1.1 times 5. So just 5.5. What are we in? Meters. And that's it. Part B, so we're just adding to it. The rectangle ABCD represents a garden of length 6 meters. We've already discussed that. Let me put that back in there. That this length from A to D is 6 meters, or from B to C. A security light is placed at point A, and it has a range of 5 meters. So that's what this sector was talking about, that the security light kind of spans over that sector. Now we're asked to find the length from B to F. So not part of the sector at all necessarily, but this length. So looking at what we have here, remember ABCD, they just told us is a rectangle, right? So that automatically means that this angle at B is a right angle. So what that tells me is, thinking back to right triangle trigonometry, I have this right triangle ABF. I'm going to bring it over here just so it's a little more clear. And what's nice about it is that angle B is a right angle. And I know my hypotenuse is 5. And we're trying to find this distance. So if I'm going back to right triangle trig, that means I can use SOHCAHTOA. I can also still use sine rule or cosine rule because they can solve any triangle, but SOHCAHTOA is usually a little bit easier. The question mark with SOHCAHTOA then is you can't use the 90-degree angle, right? So I would need to know either this angle at F or this angle at A. I'm going to focus on the angle at F, refresh on our geometry a little bit. If this is a rectangle, that means BC and AD are parallel. And this line A to F is a transversal line. I think I'm using the right terms there. But what that means is that this angle at A and this angle at F are alternate interior angles. So if A is 1.1, F is also 1.1. So I'm going to sneak in a 1.1 here into my triangle. So now I can think about right triangle trig. I am looking for my adjacent. I have my hypotenuse, so that tells me I'm using cosine of 1.1 equals my adjacent over my hypotenuse. So just like we were doing with right triangle trig, isolate your variable first, then go to your calculator. So I could cross multiply, or I could multiply both sides by 5, so that x equals 5 times the cosine of 1.1. So what is different now than what we were doing with right triangle trig before is this angle is measured in radians now. So when I go to type this into my calculator, I want to be in radians for probably the first time ever in our lives. So I'm going to have to make sure my mode says radians instead of degrees. I get that BF, or X as I've labeled it, is 2.27 meters. And in part C, hence, meaning you just found something that will be useful, find the area of the garden which is covered by the security light. Covered by the security light. We know that the security light is placed down here at A, and it has the radius of 5 meters. So that tells me that it goes to here. It sweeps the lawn for the sector, so I'll have to find the area of the sector. So part 1. And so it said the security light is placed there, but it has that range. So that means it can keep going all the way to the left here. So it could potentially, I don't know what kind of security light this is, but it could go, all the way around here. Obviously, if it's placed on a house, probably not. But in terms of the garden we're looking at, it can also include this triangle that we looked at earlier. So I'll also have to find the area of the triangle, and then I'll add those two together to get my answer. All right, so my area of the sector, since the angle given to me was in radians, I can use the formula from the previous page, which is 1/2 r squared theta. So 1/2 times my radius, which is 5, squared, times theta, which is 1.1. If I work that in my calculator, I get around 13.75. When I go to find the area of the triangle, so it is a right triangle, so I can use 1/2 times base times height. I have the base, I don't have the height. So if I want to use that, I would just have to use, it's a right triangle, so I can use Pythagorean theorem to find the height. I can also just use the same formula we've been using for non-right triangle trig. Just like sine rule and cosine rule, the area of any triangle formula can find the area of any triangle, believe it or not. So I'm going to use that formula just so that I don't have to find anything extra. But if you're not comfortable with it, you can definitely go ahead and find that height to use 1/2 times base times height. So remember, with this formula, it doesn't have to be A, B, C. It just has to be two sides with the angle between them. So I have this side of this pink right triangle. I have this side of 5. I also, in part B, remember the hence, I also just found this side, B to F, as 2.27. And conveniently enough, we had already known that this angle at F is 1.1, so times the sine of 1.1. All right, so again, when I go to put this in my formula or in my calculator, I'll definitely need to make sure I'm in radians this time since the angle is still in radians. And when I do that, I get around 5.0576. Try not to round that too much because I'm not done with my final answer yet. But my last piece is just to take those two and add them together. And when I add them together and round to 3 sig figs, I get around 18.8 meters squared. Remember, we were looking for an area, so that's why I'm squaring my units. And that's it.